Hello everyone, and thanks for watching Edupedia World Videos. So in this session of states of matter, we'll talk about density of an ideal gas. Okay, so let's see how we can use the equation of state that we studied to calculate density for an ideal gas. First, you need to understand the term density itself. Okay, so you might have studied this a lot of time before. What is density? Okay, the best way to define it is to call it as volumetric mass density. That is to say that density is nothing but mass per unit volume of a substance. Okay, so that is to say how much amount of mass will be present in 1 unit of volume of any given substance. Okay, so if you have 10 meter cube of say and a block of iron, so you calculate the mass of iron W and divide it by 10 meter cube, you will get the density of that iron block. Okay. So you can also define it as since it is mass per unit volume, you can say that it is mass concentration of a given substance. Okay, of a pure substance. That is to say, once again, like this iron block, so what I did was I divided the mass of iron block with the volume of that same iron block. This means I am talking about mass concentration. Okay, so density can also be called as mass concentration for a pure substance, and it can also be said that we are talking about volumetric mass density, that is mass per unit volume. Okay. So it is represented by a Greek letter Rho. Okay, so you write it like this, okay, and you call it Rho. Okay. So for ideal gas, how do I calculate density? So now we know the definition of density. My definition of density will be same whether you are talking about solid, liquid or gas. What changes is the process of that calculation of that ratio. Okay, that ratio of mass and volume. So I have what we say PV is equal to nRT, that is the ideal gas equation. Using this equation, since this is the only thing that we know about an ideal gas, right, from mathematical point of view. So using this equation, how do I calculate ratio of mass and volume? I already have a term of volume over here. Okay, now I need to get the term of mass. So we can get it from number of moles. What is number of moles? It is given mass divided by molecular mass. Let's say given mass is represented by W, and the gram molar mass or molecular mass of the ideal gas in question is represented by capital M. So let's substitute these values and see where that gets us. PV is equal to W by M multiplied with R and T. So just rearranging, okay, rearranging everything to get PM divided by RT is equal to W by V. Okay, where W is the mass of our ideal gas. Let's say we have a gas inside a container of volume V. So V is the volume of that container, or in other words volume of our ideal gas itself, the bulk volume, and W is the mass of that ideal gas, the gas which is present in a fixed quantity inside this container. So this means this term on the right hand side, W by V, is basically density of your ideal gas, and hence I have a formula for calculation of density of ideal gas, which is that Rho is always equals to PM by RT, where P is the pressure inside the container, M is molar mass or gram molecular mass of that ideal gas, R is your universal gas constant, and T as usual is the temperature in Kelvin. Okay, temperature T must always be in Kelvin. Now here one thing to note is that the unit of density. So if you are using SI unit, then the SI unit of density will be mass kilogram and volume in meter cube. So kilogram per meter cube, which means the pressure which you use over here should be in Pascal. R should be 8.314 joule per Kelvin per mole, temperature always in Kelvin, and molar mass is usually represented in gram per mole. Okay, but since we are talking about SI unit, you will have to convert the molar mass into kilogram per mole. So you will have to convert that gram thing into kilogram. This is a common mistake over here which students make. Alright, they forget to change the molar mass in gram to kilogram. Okay, so if you are using SI unit, you have to make that conversion. But if you are not using SI unit, say you are making calculation of density in gram per cc, which is another common unit for density. Okay, gram per cubic centimeter. So in that case you can keep molar mass in gram, but then in that case the value of R will not be 8.314. Okay, because 8.314 is the value of R in SI unit. What you can do is you can use the value of R as 0.0821 liter ATM and convert that liter into centimeter cube by multiplying it with 1000. Okay, so this is how you use this equation. Ultimately you have to remember only formula, but you have to pay attention to the units and conversion of those units from one to the other. So let's talk a little bit more about this formula of density. We have that density is equal to P into M divided by R divided by temperature. So this means density is directly proportional to pressure of the gas. Why is it so? So you can analyze it from two perspectives. First, that density is mass by volume. That means density is directly proportional to mass and inversely proportional to volume. So if I increase the volume, density will decrease, right? Because you are spreading the same amount of mass in a greater space. That means the density or the mass per unit volume is decreasing. So, and since volume is inversely related to pressure, okay, I can say that density is going to be directly related to pressure. Or in other words, in more qualitative terms, increasing pressure means what? Increasing pressure means you have the ideal gas and you are compressing that ideal gas. Okay, that means you are bringing the molecules closer, and if you bring the molecules closer, you are basically increasing the mass per unit volume of the gas. Hence you are increasing the density. Okay, also density is directly proportional to molar mass. From over here, density is directly proportional to molar mass. Why is that? This is pretty straightforward. Molar mass is the mass of 1 mole of gas. So if a certain gas has greater mass, for example, if you compare oxygen and nitrogen, so N2 has a molar mass of 28 gram and oxygen has a molar mass of 32 gram per mole. Okay, so this means for 1 mole of gas, nitrogen has lesser mass. Okay, and hence at the same condition of temperature and pressure, that is, let's say STP, density of oxygen is obviously going to be greater because its mass is greater. Okay, once you fix the amount of gas as 1 mole and you have condition as STP, the volume gets fixed. That is, there is no difference between volume of oxygen and N2 and nitrogen. They will both have a volume of 22.4 liter. Only thing that can change is their mass, and hence oxygen with greater molecular mass will have greater value of density. And lastly, density is inversely proportional to temperature. Okay, so if I increase the temperature, density is decreasing. Why is that? So if I increase the temperature or decrease the temperature, mass is not going to change. Okay, conservation of mass, right? So if I have oxygen in my container, then no matter what I do to pressure, volume or temperature, the mass of oxygen inside this container is going to remain same, and hence density will change because of temperature due to its inverse relation with volume. Hence temperature is somehow affecting the volume of my ideal gas. So how is that? Well, it is from Charles' law. Charles' law says that if I increase the temperature, this implies my volume will also increase. Hence, if I increase the temperature, my density will decrease, right? So this gives us the relation rho is equal to PM by RT, where 1 by R or reciprocal of gas constant can be said to be the constant of proportionality for this equation. Okay, so let's make a quick example. Okay, let's do a quick example using this formula of density, so we have a better understanding of this concept. So in this question we have to calculate molar mass, that is to say molecular mass of air. Okay, now see, air is a mixture of various gases, nitrogen, oxygen, CO2, and maybe some other more random gases like water vapor, argon, helium. So we don't know exactly, and hence it's very difficult to calculate its molar mass. But it is pretty simple to calculate density of any given substance. Okay, we have instruments which can very accurately calculate density of both gases and liquids and even solids. So to calculate molar mass of air, we will use its density value, which is given to us under STP conditions. So we also have pressure and temperature conditions. Okay, at STP pressure is 1 bar, right, and temperature is 273 Kelvin. Okay, so since I'm using 1 bar, this means the value of R which I will use is either 0.0. Okay, let's not use this value. Instead, okay, we'll decide it when we solve the question. Okay, so you know how to make that decision by yourself. So we have density, and we know how density and molar mass are related, right? Rho is equal to PM by RT. So using this equation I can calculate molar mass because I know pressure, I know temperature, I obviously know R, and I have been given rho in my question. So this gives molar mass is equal to rho RT by P. Okay, and what is the value of rho? Rho is given in kilogram per meter cube, which is the SI unit. Okay, so rho is given to you in SI unit. So using this criteria, let's say we use the value of R also in SI. Okay, since density is already given to us in SI unit, let's use everything in SI unit. Okay, so let's make those conversions. Temperature is 273 Kelvin, which is already in SI. Pressure given to us is 1 bar. So we have to convert this pressure into SI unit. What is 1 bar in SI? It is 10 to the power 5 Pascal. Okay, so 10 to the power 5 Pascal per bar. So here bar and bar will get cancelled, and the unit of pressure has now been converted into SI. Okay, so you solve these values, you multiply these numbers, divided them by 10 to the power 5, you will get the molar mass of your air. Okay, and that the molar mass which you will get will be in SI unit, hence it will be in kilogram per mole. Okay, so you will have to convert it into gram per mole by multiplying it with 1000. Okay, because molar mass is usually reported in gram per mole. So this is how you solve such questions. Okay, so this basically finishes up ideal gas equations and its relations in different terms. But in the next section we'll talk about Dalton's law of partial pressure. So until then, and once again, thanks for watching Edupedia World videos.